Yeah, I'm very happy to kick off this morning's session. I hope everyone had a really good time on the excursions yesterday. I know I learned a lot, including that you can get sunburn in Scotland, which who knew? But I'm sure whether you did the excursions organized or on your own, or we're here for the educational thing, I'm sure you learned something. I know I did. All right, so let's get started back to the science. This is going to be a talk largely about spectroscopy and specifically how we're ground truthing diviner data with laboratory data. So diviner hasn't been talked about a whole lot this week, so I wanted to put a slide in here to talk about diviner science. So diviner is a thermal infrared radiometer, so we're measuring the temperature of the moon. We're actually measuring moon light that's coming off the moon in different spectral channels. And with that information, we do a few different things. We take that temperature and we interpret it, and from that we can get volatile stability. We can also look at areas that have very low sources of illumination to try to determine the interior heat flow. One of the products you're probably most familiar with from diviner are things like rock abundance and thermal inertia. We get that from looking at how the surface temperature changes over time. And then the part of the investigation that I've been most involved with over the last 15 years is the compositional investigation. And for this, we're doing multispectral spectroscopy to try to interpret on the surface, as well as the composition of that plagioclase, and also the presence of really silicic materials like quartz. So diviner is a 9-channel radiometer. 2 of the channels measure reflected solar light, and 7 of the channels measure emitted thermal radiation. 3 of them near 8 microns for composition, and then 4 in the mid-infrared, all the way out to about 400 microns to measure the temperature across the full range of lunar surface temperatures. The pixel sizes is about the size of a soccer stadium or football stadium on the lunar surface, a couple hundred meters, and our swath widths are about 3.5 kilometers, at least from the nominal orbit. And diviner is also kind of unique in that we have our ability to articulate independent of the spacecraft. So we can actually look within 270 degrees of azimuth and 270 degrees of elevation independent of LRO. So I'm not going to get into how we're really using that, but we do use that to look at the moon at a lot of different angles and collect emission phase function information as well. So this is a ground truthing talk. So the instrument we're trying to ground truth is diviner, and we're using laboratory data of Apollo soils to do that comparison. The experiment we're using is called Pascal, and this is a simulated lunar environment chamber at the University of Oxford. It was at Oxford and is at Oxford. For a while, it was on loan to the University of Central Florida. But it's a very specialized chamber where we're able to heat up particulate samples using a lamp. It's under a cold shroud, so we're able to simulate solar illumination and emission off to space and create thermal gradients in the very near surface that are similar to the lunar surface. And this is becoming a capability that we're seeing more and more. I have a similar capability APL called Sable, and Pascal also has a twin at Stony Brook called Parsec. One of the caveats, and that will be important to this talk, is that the illumination angle within Pascal and Sable and Parsec is about 50 degrees. So it's not very close to normal, and we'll see that that is actually important. So if this sounds like it's a lot of work to measure the spectra of lunar soils in the spectral range, it is. And the reason why we have to do this kind of complicated measurement is because the lunar surface has thermal gradients. So if you were looking at a sample on Mars or on Earth, because there's atmosphere, heat is able to very efficiently move through that particulate. And you end up with the situation kind of like this bottom left plot, where the temperature at the very top grain is similar to the temperature a few grains down. But on the moon, we don't have this. There's no air. There's no air to move temperature around. We're in vacuum. And so most of the heat is radiated between particles. And so we have a very strong temperature gradient, can be tens of Kelvin within just a few hundred microns. And this spectrally changes the thermal infrared emission spectrum. So if you're looking at it in an ambient or terrestrial or Martian environment, you get a curve like this blue curve, relatively low spectral contrast. And then when you look at it in the simulated lunar environment, this part of the spectrum is actually colder. And so since we're looking at emission, that has lower emission and you get a higher spectral contrast. And our main compositional indicator, the Christiansen feature, is shifting position. And there's a lot of different things that can affect the strength of this gradient, and the strength of the gradient affects all these spectral features. And so we have to keep in mind things like the albedo, or on the moon maturity, since those two things are linked, as well as packing density, particle size, and of course composition. And so in order to study these materials, we do have to have these very specialized experiments. So for a long time, when we're making these measurements, we're basically heating things up to a noon-like temperature. So generally, that'd be about 390 degrees Kelvin. This is a plot showing the temperature measured by Diviner for the Apollo 11 landing LM, which it would be compared to soil 100084. On the plot, oh, it's really hard to see. This is diurnal, so this is the morning going through noon and into the evening. So this is sunrise on the left, sunset on the right. And so we'd be heating things up to about 390 degrees. But like I mentioned, we're in the experiment, we're actually illuminating things at 50 degrees. And so that would be more like 8:30 in the morning or 3:30 in the afternoon. It's an instance angle of about 50 degrees. And so the temperature that we actually want to be heating to is more like 350 degrees. That's a pretty big difference, 40 to 60 degrees Kelvin difference between those two different conditions. And so when we're going through the ground truthing exercise, these are all the samples we've been measuring. We have samples from every single Apollo mission. We have one from each of 11, 12, and 14, and then multiples from 15, 16, and 17. And this was an attempt to get the surface reference samples, so the ones that were supposed to be from the very top surface. We were creating these thermal conditions, and the box on the left here is just showing kind of what the measured thermal condition was for both this noon-like simulation and then also for this 50-degree instance simulation. And we measured all these spectra, and we felt a little bad that we haven't published these spectra yet. And so that was part of the impetus for getting this talk back out here, was to take a look at this, really get this out here, because it's a fabulous data set. We have spectra at these multiple temperatures, and they go from about, reliably from about 6 microns all the way out to about 50 microns. And so if you're interested in the spectral range, or if you're working on future missions like Lunar Trailblazer, this could be a really helpful data set. But the differences between the two experiments are relatively small. So the 50-degree incidence experiments have the Christiansen feature is slightly at shorter wavelengths than the noontime measurements. So to the ground truthing part, we noticed very early on, so this is some early data from about 2012 actually, that when we looked at the Apollo sites with Diviner, and so all the Apollo sites, it's a little faded, but you can see the side monitor, still easier to see, are color-coded here, and these are the Diviner observations for each of the sampling sites compared to the geochemistry measured by soils for those sites. It was a pretty good trend, but when we compared it to our early experimental conditions, we got a lot of scatter. And so we knew that there was a lot we needed to learn about how to do this measurement better so that we'd be able to compare it to the Diviner data. And we did get better. So when we talked about this about 5 years ago, we had a very nice linear trend in our laboratory data across all of these samples, except for this one cluster here. But we quickly discovered that that cluster was actually a different composition. So the plot here I'm showing is iron on the y-axis versus Christiansen feature on the x-axis. And if you consider also titanium in addition to iron, then this curve gets a lot flatter. And so this was a really nice result. Here we're showing that this mid-infrared compositional indicator has a very linear trend in our laboratory data when compared to the iron and titanium combined abundance of the Apollo soils. If you look back at the Diviner data at the same time, things weren't quite so clear. There was still a trend, things were still fairly tight, but it wasn't the same linear trend. And so we suggested there's additional work there to be done to better understand why the Diviner data had a different trend than what we saw in the lab. So we're looking at this now again. And so these are new analyses of both the Diviner data on the left that I've been doing and analysis of laboratory data on the right that Carrie's been doing. And I've now fit a red trend to the laboratory data and also put that red trend on the Diviner data. And here we can see that the Diviner data actually is being bounded by the same red trend, which is really good because there's lots of ways that we can get the Christiansen feature to move to slightly longer wavelengths. The chief amongst those is changing the albedo or changing the maturity. And so this was a nice interpretation. And keeping in mind, we also have that other measurement, those other variable conditions. We wanted to see what that looked like as well. The issue there is that the data we're showing here for Diviner are normalized to equatorial noon. So we've done a photometric correction. And why that's necessary is because of the thermal effects that are happening on the moon. If you just calculate the 3-point spectrum to figure out what the Christiansen feature is, there's a very strong diurnal dependence. And so these are Diviner data that have been mirrored around noon. The black data and black curve are showing what we call the standard Christiansen feature. For Highlands materials, they tend to be a little bit flatter, but sorry, for Mari materials, they tend to be a little bit flatter, but for Highlands materials, they're strongly dependent on local time. The red ones, which I apologize, kind of hard to see, are much flatter. These are a normalized equatorial noon. Not only are they flatter across all times of day, but the scatter is much smaller because the photometric correction is doing its job. So for this work, we need to figure out a way to determine what the Diviner observed Christiansen feature would be at that 50-degree incidence angle. And once we were able to do that, this is actually the previous plot, but I wanted to be able to flick between them. You get this result on the left, where now this blue trend is the fit to the 50-degree incidence laboratory data. And we see once again, we're bounding the left side of this with Diviner. So that's implying to us that at some areas, especially the Apollo 16 areas and some of the higher titanium, higher iron areas, things are behaving as we expect. We're getting this linear trend that we're observing very, very strong in the lab. And other areas, they aren't. In some of these areas, the thermal gradient is basically the same at noon as is at 50 degrees. And so trying to understand that is kind of the next step that we want to do. But like I said, we have lots of levers on what could be going on here. It could be albedo maturity, particle size, packing density, or composition. All right, so in summary, we are doing these correlations between Diviner observations and these data to enable more quantitative analysis of the Diviner data. Keep in mind, the Diviner data are 3-point spectra, whereas we are going to be soon getting much higher spectral resolution and spectral range data from Lunar Trailblazer. So I really hope that that team takes a similar approach and looks at these Apollo sites. We're happy to make these data available to them. The next steps are basically writing this up and getting all these spectra out for the community to use. We've learned a lot in doing this reanalysis that we're going to be applying to some new Diviner data products. So keep your eyes out for this. For the first time ever, we're going to do 128 pixel per degree normalized equatorial and noon composition map. Previously, we were only able to do that at much coarser resolution. And we're also looking at ways of revising our photometric corrections. As always, lab work is continuing to evolve. And so there's a lot of things we want to do regarding that, including comparing the measurements that we collected at Pascal with measurements on the same samples we've collected at APL, including not just the emission spectrum and simulated lunar environment, but also directional hemispherical reflectance as well. And I think I'll leave it there. Thank you.
Thank you very much, Ben. We do have time for a question or two.
Thanks, Ben. Awesome data set. Can you just comment a little bit on, what magnitude do you think porosity and packing has on the motion? Has there been any ability to do kind of the sensitivity studies to understand that piece of it? Because of course, that's something that's also going to probably be different from, how important is that?
Yeah, so that's a great question. And there have been attempts, and Carrie actually has done a lot of experiments in this area. And I think the result we see is that we really try to pack these things a lot, and we see relatively small spectral changes in the Christiansen feature location, but there are bigger differences in the Rostral bands and some of the other features that you'll be able to measure with Lunar Trailblazer that we can't measure with Diviner. So I think that is something that we'll be able to get more information as we have those additional data sets. But in terms of what the Christiansen feature is doing, the packing density has been really small. And it's even kind of interesting. I have this idea that in the lab, when we're pumping down our samples, we're fluffing the sample up a little bit. So even when we're really trying to squish the sample down, we're not getting that really high packing density in the measurements because those top couple particles are just going poof just a tiny bit.